Hello, everybody. So we made it up to Module 8 last week of the semester, getting very near the end. I have some things that I like to talk about in the IT courses. Right? We've hit all our major course learning objectives. I'm going to look at that in a second. In the IT courses, though, there's a lot of things that just might be useful for you. So I like to cover those. Or one of our main topics today is something that's not covered anywhere. It's about graphics, the image formats, what's going on in the background. Because to use an image, we just download the one we want and insert that in whatever program we're using. But sometimes you might want to know what's going on in the background, see a little bit of that difference. Some people might need to know it, and it's not covered anywhere. So I like to at least do a quick overview of the different formats. Some of the major ones talk about that. Put a timer on the list. I put a time allows. Just look at some more keyboard shortcuts and different things to remind you of those. Takes a while for building things up, getting practice with that. There's a lot of hotkeys on your keyboard. Right? We have way more control with that. Takes a while to learn them, so just learn one a week, and you'll know a whole lot of them by the time you finish your IT degree. You'll be really, really quick on everything. Right? Just a couple key presses to do everything on a computer. If you're the IT support guy, it always looks awesome too. In the help desk, and you walk in the room without saying anything. You push like 2 keys on the keyboard and leave. So they fix. That's just kind of fun to do. Or in an office, walk over to somebody's keyboard, going back thing, and leave, and they're knowing their computer's fixed. But it takes a while to learn all those shortcuts. We'll look at some of that. The exam reminder, I think I forgot to say this on Thursday. Please remember, I like to change schedules up. I'm not trying to trip you up, so I will send out several reminders, but exams are on a calendar schedule, which means it closes at 11:59 p.m. on Saturday, not on Sunday. So the Sunday to Saturday, what you see, the way we print out calendar, so exams are a little bit different. So please make sure you take the final exam before Saturday. The final exam is pulling from the same question banks as the other weekly quizzes, and there are not extra questions in there. So if you took all the weekly quizzes, you have seen all of the questions that will be on the final. I don't think it's going to ask all of them, but if you took all the weekly quizzes, there's no extra questions in the question bank. So I keep meaning to go back and add some. I haven't got more extra questions added in there yet. So you'll have seen all the questions. Just remembering the exams are on a calendar schedule, so it closes on Saturday, and I will send out more reminders about that. So maybe look at CRM software a little bit this week. Just kind of glance and talk about what CRM software is. That's what I like to talk about in this class. I saw it in a whole lot of textbooks on my way through school. There'd be a paragraph or a sentence. They basically just said customer relationship management software, gives the definition of it, and the normal acronym CRM, and the textbook pretty much never seemed to say much more than just that it exists. Like, okay, yeah, just some software. And out of the real world, businesses base every decision they make off of CRM software. It's one of the most important software from the business perspective. So I like to take a little bit of time to talk about that. You may have come a couple of them. Probably get to that on Thursday. And yeah, just some odds and ends that I believe will be useful for you all. Because we have time left and can talk about it in 8 weeks. And we only talk about so much IT stuff in 8 weeks. And there's a lot of things that'll be useful. We probably won't be long class periods this week. We'll probably go up to about break time. And then that way there's a little chunk in your schedule where you can finish up things further. Most people take more than one class at a time. So whether it's this class or another class, you need a little extra time to finish stuff off. So it won't be a lot of class stuff this week, but a couple things. First off, though, there is still one more major assignment due. the final project. And remember, it has two components. There's an essay component and a presentation component. And the presentation is your discussion board this week. I believe I mentioned this near the beginning of this semester, so I want to point out a couple things on how we learn. If my computer logs in, there it goes. That seemed to take a while. Going of course here. First thing I want to point out is something on syllabus. I mentioned this on the first day. That doesn't just apply to this class, but every class you take at Ivy Tech. Throw past all those useful things. Down here. So there's the course outline of record, the official documentation on what this course is supposed to cover, how many credit hours it is, all of that stuff. And one of the sections in there is major course learning objectives. Every single course you take at Ivy Tech is that's required to be in the syllabus. And near the end, you always want to come back and look at this list. And it's like the checklist, things you're supposed to do. It will say you learned. So if the course is a prerequisite for another course, when you head into that other course, they're going to assume you learned everything on that major course learning objectives. So near the end of the semester and every one of your courses, you want to look back at this list and just take a second to make sure you understand it. They're often vague and left open for interpretation. And IT technology changes, so sometimes that interpretation has to be the technology change, and we just can't teach something for a couple of years. There's one in the Java class, the applets were on there, but applets were deprecated back in 2017. And last year, I finally got the paperwork changed so that applets were no longer on that major course learning objective. So the open for interpretation in that case was just kind of, these don't exist anymore. Browsers don't even support them. We finally got it up. Well, paperwork changes slowly. Technology changes quickly. So sometimes that happens in IT, technology will change. We try to keep them as vague as we can to avoid that happening, but it still kind of sneaks in sometimes. Another way to think about it is right, school costs money. So that checklist is making sure you got your money's worth out of the course. You just want to go through there and make sure you feel like you learned everything you were supposed to from the course. And if there's something that seems to be missing, those are questions you want to ask. And we get near the end and every one of your courses, remember to check this list of major course learning objectives that will be in the syllabus in the, we call it the course outline of record section. And those are the questions you want to ask. So the other thing is the discussion board this week. Has anybody turned in this week's discussion board? I'll put on another one if not. Zoom picture in the way. Doesn't look like anybody turned in this week. So along with your topic for your paper, there's a traditional written essay that you'll send to me. And along with that is also a presentation, present that information to your classmates. The big requirement for that is do not attach files. There's still an attach button where somebody would have to download it. I can turn that off. I thought I turned it off for this class. Right after class, I'm going to actually I'll go turn that button off now. I'm going to turn that button off now so that you, that's not even an option. I thought I already turned it off for this course. More options. Oh, it's unchecked. So maybe you don't have that option. Maybe maybe I just saw it because I have that option still. But in general, downloading files is kind of considered a security risk in our modern world, right? That's something we're warned against. So I always try to make a big deal out of there's a point penalty if your classmates have to download your presentation in order to see it. It has to be visible. You can set it up as like a bunch of images, and upload the images so they can see it. You can also upload media, watch media things, and use the buttons up here. So I believe it's turned off for yours. So if you see an attach button, do not use the attach button. Use the embed buttons that are visible. Or a really good option is Canvas Studio. Oh, look at that since I'm here. Oh, I'll come back. Look at that. So over in the green navigation tabs down there at the bottom, you see Canvas Studio. This is the screen capture recording software. Kind of a nice one. Webcast-O-Matic, which had a free version that was really popular. They also paid for a version, which like doesn't put a watermark in and doesn't have a time limit. I recently did just a couple days ago, I did a 37-minute one. So there's no time limit how long it records and stuff. So it's the paid for nice screen capture software. We have that and it's built right into Ivy Learn. So obviously it works with things here. You can see I already have a bunch of recordings. Zoom has the camera occupied right now, so I can't click record, but you just hit the record button. The very first time it'll download that, and well, you can do either screen capture or web capture. Maybe if I don't start it, it'll start. So the very first time it'll download software, and then you come back and hit that button again, and then you get a box like this that says it's ready to open. And Zoom has my camera occupied, so it might not work correctly, but there we go. So the controls are here. So my recommendation for a presentation, since you got your slide deck made, and normally you talk alongside with that, I would recommend doing that for submitting that. So you can hit both, and then you got the webcam down in the corner, and just flip through your slide deck overall. Make a big video. When you hit the record button, it gives a countdown, so you can close all the other files and stuff, get them out of the way, go ahead and open the presentation. Then you get a 3-second countdown and make that recording. Pausing and leaving edit points along the way is kind of nice. Then there's a spot where you can go back to the last, like pause and restart along the way. And then if something goes wrong, you can go back to one of those previous pause points. That can be really useful, but they're probably pretty short presentations too. So you probably go all the way through. But my recommendation would be to go through that. The webcam's not required. You just do a screen capture on that. Flip through your slides and talk about that. And then when you finish it, when it gets finished, there's only a couple buttons. It's obviously hit the process and then upload buttons. Add a title. Yeah, when you finish recording, there's a box to enter a title and a description, and then an upload button. When you hit upload, it shows up on here, but you can access this from anywhere. So if I go back over to the course, I have lots of videos on there, as you saw. I can go back over to that discussion board for this week. And when you click on the reply, like you would make a normal post, under the little plugin over on the right-hand side, there's a plugin one, and I've used it recently. If you haven't used it recently, you might have to hit view all. And one of the options on there is for Canvas Studio. Should be, oh yeah, scroll down to Studio, and then just choose one of your videos. I'll just put this one. The display media tabs is a comment section for the video, shows right underneath it. But since it's going into the discussion board, we already have a comment section. So you can just uncheck that. And when you hit OK or embed, then the video shows up right in your post. So if you just go through your slide deck like you're actually giving the presentation and record it and upload it, I think that's probably the easiest way to share it with your classmates. But any way that you can think of to share with your classmates, yeah, then obviously you hit post. I'm gonna hit cancel. I was just walking through the steps there. As long as your classmates can see it. The restriction is you can't just attach your file. Don't make it so if they have to download anything to see your presentation, that would be a problem. So make sure it's embedded. And otherwise, just a quick presentation on the same topic you did the essay on. And those are due on Sunday. So unlike remembering the exams due on Saturday, so a different schedule for the exam, calendar schedule for the exam. Otherwise, the semester ends Sunday, 11:59 p.m. So please make sure you get everything submitted by then. I wake up early in the mornings, so I'll wake up Monday morning and finish up any grading. And I wake up early, so I'm usually finished grading with last minute grading and have grades submitted by like 7:30 in the morning. Earlier than most IT people wake up. So make sure you get it to me by 11:59 p.m. on everything to me by 11:59 p.m. on Sunday. The exam closes on Saturday because those are on a calendar schedule. And let me know if you have any questions and stuff. I'm around keeping my phone on all week, except for our afternoon class and the evening class. That's the only time I need to silence my phone this week. So that's the quickest way to get a hold of me. Emails, messages, and I learn. If you have any questions, just let me know. Otherwise, we're about to finish up. We hit all our major course learning objectives, but there's some other things we could go over. There's still a lot of stuff we haven't talked about. We have time left. This one, like I was saying, isn't covered anywhere. And probably because in general, so graphics, pictures worth 1,000 words, is that old saying. Right? Humans are a very visual species. Humans like pictures, not a big list of words. Right? If you're bored and start scrolling through Reddit, you're probably going to scroll past all the ones that are just pure words. And you might pause for a second on the ones that have pictures or videos, but humans tend towards the graphics. We want imagery, not descriptions. Storing image data in some sort of binary encoding was obviously a little bit more tricky than alphanumeric encoding. And so how we can represent integers with binary encoding, and then to get letters, we can just do the one-to-one correspondence. So the number 65 is capital A, 66 is a capital B. Then we go through all those. 32 is a space, and I set up ASCII code, which was then extended into Unicode. But we just give each one of our symbols a number, and then we add one more bit at the front, and depending on that bit, we know we're either looking at a number or a letter. Or the computer knows to either show a number, treat it as a number and do math with it, or treat it as a letter and display the font on the screen. Pictures are a little bit more, but people are creative and persistent. And we come up with a lot of solutions. So I want to kind of look at some of those differences. I have some, the picture that I'm going to use as sort of examples. I drew this really quick. I drew it in like 3 minutes and made 5 different versions right before class. It was after 150 that I realized I forgot to draw it and then needed to open it. So not a nice picture here, just a basic one we can do and I can quickly sketch out. So just a quick couple rectangles with the colors and circles. So it looked like a tree and the sun and sky. But different formats. 4 of those 5 preview right here. I can open this one with Chrome and see it's the same picture. So all 5 different versions of the same picture. And if we needed to use one, we just grab the picture and like throw it in our Word document. That part's easy, but like what's the difference between these? That's what I wanted to look at today. So I'm gonna go over to my simple text editor and start here. Oh, simpler than that. Notepad, most basic text editor on here. And I'll open up some files. So file, open, and let's see which one to start with. Switch so I can view all files. So we got a bitmap, JPEG, a GIF, a PNG, and an SVG. I think that's the order I was thinking about going and doing it. So I'm gonna open up the bitmap first. Obviously, it couldn't turn that into text, but it tried. Notepad, the simplest text editor only opens text, so it just grabbed things 16 bits at a time. Like, oh, open a file. Well, I don't open Unicode files, so I'm just gonna grab things 16 bits at a time and see what happens. It ain't quite come through correct, but we can see a few things here. A big section of repeating that symbol. Then we switch to a different symbol, and there's a section of that symbol repeats for a long time. Word drive on? Oh, word drive's totally on. Then we get to something else. Looks like there's a pattern, but it's definitely a repeating pattern. See a pattern repeating over and over and over again. And scroll down quite a ways, we should see a slightly different pattern that repeats over and over and over again. So it looks like it starts here, and then we have a slightly different pattern that repeats over and over and over again. So lots of patterns showing up in that one. Another one. Open. We're in the same folder, so maybe the JPEG. JPEG looks a little bit different. We have some words there at the beginning. It did find a few letters at the beginning. Some blank space where you apparently couldn't do anything. When we get down here, and it looks like a whole bunch of gibberish, but we don't have that huge section like we did in the bitmap. I know what's here. There's this big section of the same thing, and then we get into this small section here that shows a bunch of gibberish. If I scroll down a little, we see more of this, followed by about the same amount of characters. Different characters, but about the same amount. It's the same image data, and we keep getting that. Things are coming across in chunks that size. We have to really dig through and find repetition. It's not very repetitive. We'll see it here in a moment, but what is those differences? So like here, why do we have all these obviously repeating patterns in large chunks? And here, why do we have much smaller chunks? That the size seems to be repeating, but the characters it's showing is very different. And we'll see that on all of them. So if I go file, apparently this opens a new tab every time I do this. So I open the GIF. Bunch of gibberish. This kind of looks like the last one. Things are coming through in chunks, but they're not necessarily evenly distributed or anything. It's hard to, we're not going to pull information from this. I just want to kind of look at those patterns. The ones that have repeating patterns, the ones that don't have repeating patterns. I guess there's one more to open here, so open the thing. Oh, there's two more to open. Ping. Things are spread out. And if we start scrolling, we won't see any repeating patterns here. Everything in this one is unique. Just because I already know it's there, but a bunch of gibberish. I guess it looks, we see a big chunk like we saw earlier. So it's not just completely scattered. We're back to like we saw in the bitmap where hard to tell what that data means, but it is organized into nice little chunks where we have the same thing repeating like we have in our picture, right? All those big sections of blue, all those big sections of green, there's definitely something repeating there. So those repetitions probably relate to that, and we get stuff like that. And that's the end of the file. That was really short. None of the others, I scrolled and scrolled and scrolled and never reached the end of the file, and this one's only this long. So way shorter. That's going to make a difference. One more to open. Close this tab. We'll come back and look at these, and then the last one is the SVG graphics. And this one's in human readable form all the way through. Oh yeah, we saw HTML in module 5. I know at least one person has already had that class, so that we had those tags that we put in. So instead of the tags about our paragraph and stuff, here we have a tag about a rectangle. Another tag about a rectangle. And then ellipsis, which one of those has got to be the sun, and one of them's got to be the treetop. And it's human readable. So yellow is an even mix of red and green. So this color right here that is red is FF, which in binary is 11111111. So all on switches. Red is fully turned on and green is fully turned on. So this must be our yellow sun. And this one, the red's turned. We have 8 bits, so 2 hex digits. Remember talking about binary earlier, and then hexadecimal is four bits at a time. So 8 bits of red, and then 80 for our green. So 01000000 is the amount of green we have, and everything else is zeros. So that must be that green treetop. But it's all human readable. We can identify what's going on in this one. So drastically different things, but all sort of the same picture. I want to talk about those differences. It never really shows up anywhere, and kind of at least give an idea of what's going on with those. So the first one, keep that open so we can come back and look at it after we see the patterns, what's going on there. The first one, basic format is bitmap. Collection of instructions. What color each pixel is, or should be. This is what you would probably think of intuitively. This is great big grid. I'm going to simplify it a little bit. I'm going to draw as many pixels as the screen has on it. But for our pixel, we have a bunch of blue up here in the sky. We have that yellow circle for the sun, surrounded by some pixels that are going to be blue. Somewhere we can use a green top for the tree, blue around the top of that tree. I'm going to do BR, the wrong spot, the trunk coming down on the tree, and then a bunch of green down here. So kind of simplified. I guess I could have drawn a few more, so more than just one pixel of yellow. But pixel by pixel instructions of what that picture should, what color each pixel should be. And part of the reason I like to talk about this is to answer those questions. So if we needed to squeeze this down, it's like, oh, that image is too small, let's make it smaller. That image is too big, let's make it smaller. And went down to a smaller grid, which the ones I have there is not a very good number. We went down to a smaller grid. We can drop pixels, right? If we squeeze this down, because that's the only size smaller would be a 2x2 or 2x, oh, there's 3. So we could drop some of these pixels. So like this row here, I'll say that row is extra. So when we make it smaller, we can still have pixel by pixel instructions. BBY, BGBB, GG. I'll drop this row, GGG. So we still have enough to see that picture. Obviously, with lots of pixels, there's still going to be a whole lot of information there. So it stays clear when we make it smaller. But if we tried to scale it up, we can't, the computer can't add things in between. If we make it bigger so that what was originally 1 pixel here covers 4 pixels, that one pixel has to stretch out across all 4 pixels. The computer can't add information into the other ones. So that's why bitmaps get blurry if we stretch them out, or pixelated. If you like pixel art, right? A lot of people like that for nostalgia purposes. A bitmap is a great way to make pixel art. Make your thing small, make your picture smaller, save it as a bitmap, and then scale it back up, and then it's going to pixelate quite a bit. So we even have control over how we lose clarity with those. But probably somewhat intuitive, just set it up as a grid like our screen, and then just send an instruction for each pixel. Next one, joint photographic experts group. So JPEG. Sometimes in the extensions we drop the E. The joint photographic experts group. That's the company that made the format. Is what that was named after. This one has a bunch of big math terms, so I'll try to kind of explain what's going on, but well, I'll write it out. Color data is stored as a discrete cosine transform. Those last 3 words come from high-level math classes. So discrete is distinct values. So computers are distinct machines. We either have a 1 or a 0, and we don't have the stuff in between. But an analog, like old radio, the volume knobs, turning the volume knob, you have every point in between those knobs. Or a volume knob would be a good example. Some volume knobs have that smooth everything in between, and other volume knobs will like click to each particular number. So the ones that we click into place, that would be discrete. They're separate values. We don't have the entire spectrum. Cosine is one of the ways of representing a wave in mathematics. In particular, cosine is one that starts at the top and goes up and down like that. And a transform, or a Fourier transform, is when we put a bunch of waves together. I got the colors. I have red, green, and blue here. So we take 4 different waves. Maybe we have some red. I'll draw something like that, so that it starts spread out, then it gets closer together. I was thinking spread out when I drew it, but I didn't really spread it out much afterwards. But a wave that sort of changes on each crest and trough. It's not a perfectly smooth wave. Then we'd have some green. And cosine just means we start the wave at the top. We could also at the top or the bottom, as opposed to starting it in the middle. So like this is cosine. And if we start it in the middle and then go up and down both, then that's a sine wave. For those who have not had trigonometry class. The green one, maybe I'll spread this out quite a bit. Something like that. It's real spread out real far. Then we have some blue. I'll put lots of blue here. Something like that. And then we have grayscale. I'll just do a little bit together. So we have, so those are cosine waves. Discrete has to do, since we're in a computer, we have the ones and zeros. So it wouldn't be a perfectly smooth curve. We have all those ones and zeros, so our curve would actually look something more like this. So actually our wave looks like this. That's the discrete part. And then transform is a Fourier transform is we can superimpose these together. We can add them together. And then all the parts where there's a crest of the wave, those are the crest of the wave we're going to add, and the troughs of the wave we're going to subtract. So if I choose like a little section here, so that's at the top of the red wave, so we're going to add quite a bit. I'll put 2 plus signs. And looks like we're at the bottom of the green, so we're going to subtract quite a bit there. So I'll subtract. Looks like it's coming through about the middle of the blue. So we're going to add just a little bit back. And down here, we subtract. So we do that for the whole wave. Every crest and trough in the wave, we add those together. And the result is going to be something that looks like a sound wave. When we add those together, I'm going to write the word not accurate here, because I'm not going to sit here and do a Fourier transform on those waves I just drew, but we get something when we add them together. The cosine, so they all start at the top. So I know that top is going to start up, but then we end up with something that looks like a sound wave after we add all those pieces together. It's not the same thing as a sound wave. A sound wave is an actual representation of that sound wave. This is in no way related to the light wave. We just stored these as numbers. We just, we found the middle of red. So the halfway point of having all red versus all zeros. So that 0, 0 to FF value, when we look at it as RGB colors, hexadecimal. The halfway point, we put that in the middle, and then our wave goes above or below. So we just have a bunch of numbers. It is in no way related to the sound wave, but it looks like a sound wave when we draw it out. I think most people in our society have seen pictures of sound waves, right? So it helps to visualize it that way. And then also the reason the JPEGs get blurry relates nicely to a sound wave. Because like in the old tape audio, when that tape would wear out, the sound wave starts to get messed up. Get stretched out, might get shrunk down, depending on what the heat did to the tape. It can change in different fashions. That's why if we have a JPEG picture, it's going to look wonderful. It's going to have the best clarity all, as long as we don't mess with the size. If we start messing with the size, whether we get smaller or bigger, it's going to get blurry, just like a sound wave would get distorted. Or playing back audio. If we slow down audio, it distorts, right? The voice gets lower, but it also, some of the other qualities of the voice would get changed from the original one or speeded up. So that's why JPEGs, we can't change the size at all unless we're going through special software. You need to actually load it back into something that can recreate the waves. You want to change the size, you go through and go back to the original data. That's called a Fourier analysis instead of a Fourier transform. When we have separate pieces and put them together, that's Fourier transform. And if we start with that combination and break it down to the pieces, that's a Fourier analysis. We're running through software that does that, and then we have those original pieces that we can put back into a slightly different size JPEG image. 20 years ago, that was the one that was clearer on Macs. Somehow they still run on that reputation of their graphics being better. JPEGs were clearer on a Mac 20 years ago. Has to do with the grid of pixels. Our screen is a bunch of a big grid of pixels. So we have like a red line, the computer's going to estimate where those are. So on a Windows machine or Linux machine, we use any number. We use floating point numbers wherever that lands because it's a lot quicker. So maybe it's going to look at all those dots and estimate that, oh, looks like those are closest to that line. And it's going to draw it on that line. But then if we open it on a different machine, the other machine might decide that this is closer to this line. And then our line's going to look like this. We get that blurry edge. 20 years ago, that was happening. Apple, however, only allows integers for the pixels. So if we wanted to put the dots on a screen, this is when we create the images. When we create the images, Apple only allows images, or Mac OS only allows integers. So a straight line can only be a straight line. That's been fixed over the years. That only affected JPEGs. But for some reason, Mac still seems to have the reputation for that. Even though it never affected bitmaps or GIFs or pings or SVGs. SVGs always have crystal clarity, no matter what screen we draw them on or what size. We'll talk about why here in a moment. Lots of different formats. So with those two, though, come back over to those text files that I opened, or open those in text files. Now looking at the bitmap, do you see how that kind of relates to the big grid? We have that pixel information. So all those big repetitive sections are the grid of pixel coloring, which is all because it's trying to show Unicode, which is 16 bits, but it's colored RGB. Each one of them is 8 bits, so each color is 24 bits. So we're slightly off from opening it in a text editor. For the JPEG, sometimes we can look at these patterns and kind of see these repetitive sizes. I guess if you look at it sideways, look at the ups and downs like a wave. Some really tall peaks, really tall or really shallow points going back and forth. Not exactly accurate, but that's where that pattern is arising from when we try to view the JPEG in Unicode. Some people might need this. I've used it a few times in software development, needing to work with images and change the format of the images. If you need to change the format of the image, you have to actually go in there and work with the data of the image and do something different with it. What's next on the list? Oh, GIFs. Or GIFs, however you want to pronounce it. Graphics interchange format. Or GIF. So I think that I was going to be called. Hopefully it won't affect talking too much. So it's a special type of bitmap. These can get pretty accurate imagery. Most people use a bitmap anymore to shrink it down and then scale it back up until they get pixel art. So the most common use of a bitmap is specifically to mess up the clarity on it, but it can get pretty clear. We can get some decent clarity on it. But both of those are big. We need information, like 24 bits for every single pixel in that image. And programmer pixels do not line up with screen pixels. They haven't since like the 1980s. In history books where those cathode ray tubes with black backgrounds and green lettering. That was the last time programmer pixels and screen pixels were the same. So we want to have lots of pixels so that if somebody with a 4K screen opens that, they get clarity. It still looks, the bitmap still looks good there. So we have lots and lots and lots of pixels there. The 24 bits a piece, that really adds up. A lot of data. This is a bunch of math equations. It can get fairly large, depending on the image. But we want to keep it precisely that way. So we have this large image that needs to transfer across the network. Things can happen transferring across the network. That was the biggest thing with these. That we can get them transferred across the network, but if anything went wrong along the way, right? If that bit went off, then our entire wave is messed up all the way through. We need the whole thing connected in the original format. We need it to come through perfectly. So not great for transfer. So when the internet started taking off, obviously the goal was to find some formats that transfer really well. GIFs or GIFs, depending on how you want to pronounce it. Pretty sure either way, people would know what you're talking about. It stands for graphics, so I always just go with the long G myself, and people seem to know what I'm talking about, but I hear the other one I hear the other pronunciation just as often. So the first idea they came up with is a special type of bitmap that defines, that's supposed to be letter D, it didn't look like it, defines a restricted color space. So we got this bitmap over here, the idea of a bitmap. Have you ever seen a picture that uses every single color there is? We don't need all those colors. So by transferring the need for the ability to open up every single color there is, there's a whole lot of extra stuff coming with that. So let's get rid of that. So we look at the picture it is and just restrict it. So here's the space of all possible colors. And then from our picture, we just need this little bitty subset right here. Our colors. We only need a couple of those. It makes it a lot smaller. Bitmaps aren't particularly huge, but if we make them smaller, that can be useful. This didn't last very long. The next one we're going to look at pings. Yeah, I'll go ahead and read the name. It's going to be written in a moment. But the next one is portable network graphics. The name for that, it was built from the ground up explicitly to transfer across the network. So it replaced this within months. Right, more than one person was working on it, and it kind of showed up. So GIFs would have faded into history, long forgotten, except for one little thing. That's that we made this file really small. Well, if we took, I'll use numbers 100 kilobytes. Say we have a 100 kilobit file, and we turn it into a 10 kilobit file. There's a lot of extra stuff we can do in that file, that extra space. One of those things, somebody come up with the idea a few years back, that why don't we just put several images in the same file? If we're taking away 90% of our file space, 90% of what's in that file, and we only have 10% left, then we could put 10 images there and have the same size file and create a little animation. So these made a comeback because that small file size allows us to make an animation of bitmaps. And it's not a big huge video file. It's still it's still a reasonable size image picture. There's just several images in there, so we can play through them like an animation. Just add a little clock in, and it's still reasonably small. Otherwise, GIFs would have been long lost to history because they didn't have too much of a heyday. It was just one of the ideas that came out. They were the ones that This was also the first one that allowed transparency. That's probably the only reason it really took off. And they figured out that they could just leave colors off. It's bitmap, so if we just say that leave this one blank, then there's a transparent pixel. So they did transparency that way. Was probably the only reason they took off to begin with. Is it okay if I erase this? There's two more to talk about, so I'm just going to go ahead and erase the whole board if that's okay. Oh, I need to move the camera back over. Good. I'm going to start on this side and show people up there. So erasing the bitmap one, the camera wasn't pointing here when I did that. So since GIFs are a type of bitmap, the original transparency is they would just erase what was in certain pixels and then leave it there. And then we could see through that pixel, we could see whatever was behind it. This one's kind of complicated, but hopefully that made sense. It's a giant math equation. It doesn't store the grid. It stores a giant math equation to recreate that, but everything has to be perfect with those. The next one to look at is portable network graphics. Or our ping files, .png. So this is early 90s, networks are really taking off, the internet's taking off. We want to transfer pictures. None of the formats, well, they get across the internet, but it might take a few tries, especially in the early days when it was coming across just very, very slowly. You heard about those numbers. In the 80s, it was 28 kilobits per second. In the 90s, when the internet was really taking off, about the time this, we were up to 56 kilobits per second. Really small, but it seemed like a lot at the time. It was coming across the phone line. And like always, reporting the number is the optimal situation. So it would get as high as 56 kilobits per second. And you usually weren't getting that, right? Kind of like Spectrum when, if we look at the paperwork, Spectrum tells us we all have, what is it now, 42 gigabyte internet at our houses. But if you pull up your meters, you're probably getting more like 7 or 8. Nowhere near what the advertisement says. So we needed something to really work with the internet, and that's what people look for. That remember we looked at the TCP/IP protocol, in particular TCP. We get across the internet. We break our data down into little packets. And then from the internet protocol, each packet finds its own route through the internet to be reassembled on the other side with the OSI model, all the different layers. You'll hear a lot about that over and over again anyway through school. Obviously, the way we transmit data across the network is very important no matter which direction you're heading in IT. So this was intended from the initial design, for speedy transfer. On a TCP IP network. Image data is described in chunks. That is the official word, going back to the original documentation for the proposal. It's described in chunks, which they use a different word, but remember the packets in the TCP protocol those chunks should relate very nicely to packets. So when every time we store it, we're ready to break our image down, send across the network. And those chunks are either ancillary or critical. Critical or ancillary. And ancillary is not a commonly used word because of the situation. Everybody see what ancillary means here is the opposite of critical. So again, with the network, remember those checks, we had that checksum bid, something went wrong, send it again, something went wrong, send it again. Well, we can decide whether we want to request another one or if it's worth it to ignore it. Like, okay, yeah, we missed that, but it's not important. It's not important enough in this image. We can live without it. Send again if you get a chance. So the opposite of critical. And we actually, all of that stuff is defined that way. Then pixels are grouped in layers. Layers that reference chunks. So where do we put it? So for this picture, I'm gonna, so we have grayscale. Over one side is very black, and spreads out, and white on the other. So some number that represents how black or white it is. Then we have some red data, which I can color code. Some stuff's going to be red. Some stuff's going to be green. And some stuff's going to be blue. And then there's other parts in it. I'm just hitting some key points here. And then we have a position chunk. So here's our chunks. I have a chunk, and there's more than one. So we have chunks of grayscale and chunks of red, chunks of blue, chunks of position. And then our layers I don't know what those pictures look like. So if I open the ping, so we have a big green circle, that blue, yellow circle, and then the green down the bottom and the brown. So to represent that here, we have a layer that just forms a nice little circle. And this is going to reference the red and the green. So yellow equals red plus green, and then blue defines how bright it is. So there's a circular layer that references a yellow chunk, basically, by tying into both of those, along with some point of grayscale. It's a nice bright sun in the sky, so it's going to be way over on the white side of the grayscale. And it's going to come down and maybe right around there, reference a position point, reference some position chunk. And then there's an entirely separate layer over here. With voids left in it. This one going to reference the blue, some grayscale of the blue, so how light or dark is that? And it references a position chunk right up here in the corner. And there are actually holes in that layer. So the transparency in a ping is different, is slightly different. We just, we can leave holes in there. Where do we have then we have a scattered around layer, something that's sort of dispersed. This layer is going to reference the green chunk, and maybe from the upper, I'll point to the upper corner there of what would be the whole picture. It puts the upper corner over here somewhere. Maybe here, about where that treetop is. And we just break it down that way. And this stuff is going to align perfectly with the TCP IP protocol, our TCP packets, the format we take in transition. I guess there's only one more. Then we have a little square chunk for the tree trunk, which is going to be red and green and blue. Have a little bit of everything. Reference some position down here and grayscale, but the lines are getting a mess there. I think y'all see where that's going by now. And we have it all in separate pieces, all designed from the beginning for transmission across the TCP protocol. So it's already designed to go into the packets in that OSI model, along with all the data that we're transferring. Get great clarity. Can scale it down, and just like a bitmap, if we shrink it down, we can lose some of this data and still be okay. We could make this circle smaller and we'd still be okay. If we scale it up, when we get a little bit blurry. Sometimes you can scale it up quite a bit before it gets blurry, because maybe it was created huge, so we kept some of that clarity when we scaled it down to middle size. And you scale it up a little bit, you get that clarity is still in there. So there is a threshold where once you scale it down to a certain point, you can't scale it back up. You lose clarity if you scale it back up. But a different format of it. I just wanted to kind of cover all these somewhere because it's not talked about anywhere. The graphic art people, graphic design people over in visual communication school, they don't even cover it. We just grab the image we need and use it. I have used these things, had to get in there and work with the data a few times with software development. So if I say that way, you might have to. Or on a network, if an image isn't making it across the network, you might want to know why. And that's going to involve knowing what's going on with that data. So I can't guarantee that you're not going to need it, but and we had time to cover it. That way you see it somewhere. The last one was that one that was in human readable form. Scalable vector graphics, or SVG. In particular, vector graphics. So scalable vector graphics is kind of the standard for how we would represent two-dimensional vector graphics. Three-dimensional vector graphics, I'll look at a version of that in a moment. Internal to the computer, they're exactly the same. The difference between them is how we present them to the human in the text file. When we go from that, what's in the RAM and CPU, that actual binary stuff, and turn it back into a form humans can work with. For two-dimensional, we usually go with SVG, which is a markup language. We saw HTML earlier this semester. Fairly easy for humans to work with, especially if we're not writing the tags, the computer's writing all those tags. They're just there and we're reading them, then it's pretty easy. A similar thing, but what this is images stored as points, lines, and polygons. Lines, curves, I'll put that on there. Curves and polygons. Right, Matt. We don't store the image, we store the equation that represents that image. So graphics are like graphing in your math class, like the XY axis and all that. We just have lots and lots of pixels. Every pixel is a unit. So except Y usually goes down, but in general, it's just like graphing you learned in math class. That's why they have the same. Graphics is the noun that comes from graphing. So we just store the equation. So like in math class, and I'm going to do it like math class, we have our X and Y axis. On our screen, the numbers go Y, positive Y is down. I heard two different descriptions and both of them make sense as to why. One reason I've heard is that, well, when screens that we still use, the ones that translate came down to is that they've constantly built off of, those were created in the Apollo projects in the 1960s. So they made the simulations going downward. The other one is lines on page. Line 1 is at the top of the page, so we follow the lines on the page. Both explanations make sense. I don't know which one it actually is, but one of those two things. I'm going to draw it like math class because this is how you're probably used to seeing math teachers draw it with the Y up. And then we can store things like somewhere over here, x squared plus y squared equals r squared. Everybody seen that equation before? Well, it's like the Pythagorean theorem. A squared plus b squared equals c squared for a right triangle. And if we went and tried to draw every possible right triangle with that same length of hypotenuse, we'd get a circle. So when we want to switch from triangles to circles, we usually switch to x, y, and z to represent every possible right triangle we could draw in there. But we have an equation representing a circle up there somewhere. We have another circle over here. And then also a little bit of data. Make that circle yellow. Then over here somewhere we have x squared plus y squared equals r squared again. Slightly different r, but sort of an equation. Make this one green. And coming up to that, I'll write it out horizontal. Y equals mx plus b. Everybody remember seeing that? Having the equation for a line drilled into your head somewhere along the way in your math classes. Just have an equation for a line. And in particular, in this one, it's brown. We can also do rectangles. Rectangles would be like a polygon where we store 4 points. We have some XY coordinates here. And if we have another point over here, I'll call it X2, Y2. And that tells us how wide it is and how tall it is. So 2 points is enough to store a rectangle. So then we'd have a green rectangle down here and a blue rectangle up here. And then there's the equation. There's the equations to represent that simple picture. We don't have to worry about clarity. We never store any size data. Our size is relative to the screen we're showing it on. So whether we want to see it really big or really small, we never don't lose any clarity. I guess we can see that here. Oh, whoops. I didn't mean to double click on that. Open that with a browser that has zoomed in and out. Well, obviously, most of our pictures, anything except a JPEG, we can scale it down and still get clarity. But we scale it back up and keep going until the browser won't scale in anymore. You see that's still a crystal clear edge around that circle. We keep our clarity. All we have is the equation. I'm going to circle those two words because to keep it consistent, more often than not, we use those two things for both 2 and 3D. Right. I put everything up there, sort of points, lines, curves, polygons. Yeah. So 4 things. We basically get rid of 2 of them because points and polygons are enough. So points are like we use the word vertex. It's just a point in space. And I'm just going to draw a triangle. Polygon refers to a shape. I mean, many sides, so a triangle is the easiest polygon. So we have three points in space, or vertices in space somewhere. Maybe 2-dimensional space, maybe 3-dimensional space. They would behave kind of the same way. It's vector graphics, so it's still part of the equation there. We would connect those with edges. And whenever we fully enclose an area, we fill it in as space. So that's how we store, that's how these are most often stored. That one I drew, I specifically know that one does have curves in it. That's why it's a smooth curve. If we try to do a polygon that had a finite number of things, eventually if we scale it up big enough, we're going to see those sharp edges. It's not a perfect circle. The one I drew from right before class does have a circle that used all 4, but typically we would do it more like this form. Something I can. Yeah. I may have to run some code here. Actually, I'm just going to open this file. There's already 215. This is kind of the last thing I was going to look at. So we saw for the 2-dimensional ones, we usually use scale SVG, which is a markup language, kind of like the XML. And actually, you saw I open that with the browser. So if you're making an HTML page, you can just put SVG graphics right in there and not have to worry about scaling and clarity or anything like that. For 3-dimensional ones, it's slightly different. I have one over here in Python. I happen to have one on the computer in Python. We can look at it real quick. This one's going to look like a mess because this is a full human. Actually, I guess any of them would work. Earlier this summer, I was improving my add human button in Blender I created a few years ago. Happens a lot coding video games, so I just made one button to insert my character to not have to spend several hours doing it with the thing. So there's a bunch of stuff going on, but then this verts, abbreviated form of vertices, edges and faces. If I turn on word wrap, you can see what happened to the scroll bar there. There's lots of vertices making up a human shape, obviously, but we have all these vertices in space. And a vector, a quick way to think about that, we're going back to the math class description. Instead of in class, maybe this is 1 over and 2 up. Right, that's what you would have learned in math class. The point 1, 2, come 1 unit over, 2 units up, but we're locked in space there. So that has very specific meaning. Another way we could describe that is the arrow that starts at the origin and goes 1 unit over and 2 units up. So the arrow that starts at the origin and points at that, because then we can just change our starting point. So, okay, instead of starting there at 0, 0, start way over here at 10, 20. And we can still find that same point, and we move them all that same direction. Move all those arrows, and then we still have that same shape someplace different. That's the starting idea of what a vector is. The basic idea is it has multiple components, multiple parts to make up one value. So instead of each number being individually, colors are a good example. We have red, green, and blue. And if we take one of those away, we don't have the same color anymore. We need all three of those numbers in order to get that particular color. So we can't separate them. So same thing here. Each one of those points is made up of an X, Y, and Z coordinate. It's at some spot in space. So it's in a list, and in computers, when we put lists together, we usually start at 0 instead of starting at 1. Has to do with where it's at in RAM. The spot where the data is in RAM, plus 0 gets us to the beginning, not plus 1, the way humans intuitively count. We go to the beginning, then plus 0 from the beginning tells us where the first one is. So we have this element 0 in our list, which is just a point in space. Then element 1, element 2, I'm turning word wrap off. So we have a whole bunch of points in space. And I just use spaces. We could use either edges or faces. If we fill in one, then the other one is obvious. Okay. We start putting edges in there, it's obvious what face kind of falls in between them. Or in this case, I went with faces. If we put faces on there, it's obvious which edges need included as well. So the computer can figure out one of those other two. And then these refer to those indexes in that list of vertices. So to create this face, the 912th vector that we loaded into that list of vectors is going to connect to the 884th one, the second one, which we could probably get to that in the list, 0, 1, 2. So then this is the third one it connects to. I'm not going to try to find 900 and something, 800 and something in that list. 2 is easy to find. And then the 96th one in that 96th one in that list. We're going to get all those into a face. And then that's where we get this shape. And we do that lots and lots of times and put together different polygons. That one has 4 points. The next one also has 4. This was made in Blender. Most of them have 4. I did do some customization, so there are some longer ones. Somewhere between, we need at least 3 to make a triangle. Otherwise, we don't have enough to close things up, right? So somewhere between 3 and any larger number. This is a shape that we can fill in, and then we put those shapes together to make the thing. So this is what it looks like in Python code. We saw Python earlier this semester. Most people would look at it as wavefront, which is the same thing, only it's in a normal text file, and we have all the vertices. Each vertex gets its own row in a text file, and then at the bottom, each face gets its own row in a text file, but the same thing. We just refer to the vertexes in a particular face. That's how we deal with that in 3-dimensional, kind of how the graphics build up. That went about 5 minutes longer than I intended it to, but a quick pass at graphics. You may never need that knowledge, but you might. Sometimes it shows up. By heading towards game development, you'll definitely need that last part. That's very important for game developers, which is why I had that handy. I've spent most of the summer working on game development stuff. It's tons of fun. I have as much fun making games as playing them. Perhaps more. I have a lot of, it's like a giant puzzle in itself. A game or a puzzle in itself, but that's a different point. Anybody have any questions about that? Kind of makes sense. Maybe clear up why like JPEGs blur differently than PNGs when we start resizing our image. That's probably the one takeaway that I could say count on using from this. When you're looking for the file to use in your document, knowing, and you see PNG or JPEG images, knowing which way they're going to blur up, or a bitmap, which way they'll blur up or stay clear, depending on the size you need, that might make a difference. Otherwise, that was all I wanted to talk about today. This week's going to be extra stuff. On Thursday, I have small things. So there's lots of pieces like that. All the stuff. The rest of the stuff I have on the list for odds and ends, and we'll go about the same time, to about the point that we would normally take a break. And just just a bunch of small parts that I believe will be useful for you all heading into IT. Since we have time, might as well cover it. Otherwise, quite a bit of time left on our scheduled block for today. Please use this time productively. Relaxation is productive. Resting is going to be more productive than if taking a break is always going to end up more productive than if you would have tried to force yourself to push through the break. A lot of people seem to miss that point. But whatever will be most productive for you, please use our time productively. If you have past due homework or something in this class or another class, it's a good time to get it in. The semester ends in a couple days. You have a final exam. Now might be a good time to take that final exam. And that way you know you have it done by Saturday. You don't have to worry about it just approaching the last minute or wake up Sunday morning and realize that you forgot to turn that in. Yeah, actually, now is probably the best time to do that. But if there's no questions, that was all I had for today. I'll see y'all on Thursday. Everybody have a great afternoon.